Okay, so now it's my pleasure to present Michael Roeckner with the last talk for today, please.
So I need just a second to connect my iPad. Just a moment. Okay, so this is a joint work with Wei Liu and Jose Luis da Silva from the University of Madeira. And the title is Strong Dissipativity of Generalized Time-Fractional Derivatives and Applications to Quasi-Linear Stochastic PDE. But of course, because of lack of time, I will only talk about first part, so to speak, of the talk. And this connects very well to what Vasily just explained to us. So this is the structure of the talk. The generalized time-fractional derivatives as generators of C0 semigroups and their strong dissipativity. So you've seen already that these time-fractional derivatives are generators of semigroups and Markov processes. And our approach is to use this to solve this nonlinear quasi-linear PDE. Okay, but I will mainly concentrate on the second point, so therefore it's very close to what Vasily told us. However, in my case, I do not consider these generators, which are fractional time derivatives, as generators of Markov process on time in the time axis, but generators, generators of semigroups, I should say, with values in some Banach space, and then use that in order to solve these equations. Okay, and so I basically only talk about section 2 and give a little bit of motivation by having a glance at section 3. Okay, so that is the kind of equation we consider. So it's just a time, we have a fractional time derivative, and here we have some operator, and we do it first of all in a completely general evolutionary framework. We work on a Gelfand triple with a Hilbert space H separable, and then a Banach space embedded into it densely and continuously, and then we have the embedding of the Hilbert space again to the dual space of the Banach space via identifying H with its dual space. Then these operators are depending on time, and they go from the small space to the large space, so as usual in theory of evolution equations. And then let me just write down the fractional derivative. So we're given, so that's completely classical. We are just given a locally integrable function on 0 infinity, positive, non-increasing, and without loss of generality, we can take it right continuous because we just putting this thing in an integral, so this doesn't matter. And we always assume that at infinity goes to 0. So that's a typical generalized time fractional derivative, includes many examples. On the next page, I will, later on, I will briefly recall that. And then, so we want to solve a certain equation, which is on the next page. Okay, so we want to find a path, so solution to an ODE with values in infinite dimensional space. So this xt now takes values in the space V where the H is acting. And I want to say this operator H is nonlinear. So it could be the Laplacian, that's a simple example. But main interest of us is, for instance, when this is the porous media operator. And so this would be the equation with the, so in the deterministic case, so we just have on the right-hand side some function of t in this large space, but we can also put the stochastic into the fractional one. But I don't want to go on to this at all. Just want to, so this is just to show you our motivation. And then, so typical example for A is a porous media type operator where the Laplacian is even fractional. So that doesn't matter at all. It just works all in this very, very general framework, because this operator here is a very nice so-called monotone operator with certain coercivity properties. So our general theory applies immediately. And on the right-hand side, this F, so in comparison with the original one, can also depend on the solution, but it must depend in the Lipschitz way. However, this operator is typically non-Lipschitz, because Lipschitz operators that are Lipschitz basically don't appear in nature. Lipschitz means continuous, but of course they're very useful in approximations. But for instance, here definitely you don't have this Lipschitz property of the operator, and the same also for the P Laplacian, and we have many other examples. And even we can do this when we live on a fractal, so it doesn't matter. Yeah? It can also be we just take an L2 space over a fractal, and then we can define this operator using the fractal Laplacian. So there's also fractionality in space allowed in applications. But in general, we just look at this very simple framework of a Gelfand triple. So exactly this. And now what is the main idea? The main idea is that you do not consider this equation on state space, but on path space. So that means you look at the corresponding Gelfand triple, which is just the space of path on with values in this space. So we look at this space. Alpha is bigger than 1, so maybe I should just add this. So alpha is in this interval 1 to infinity. I'm sorry, so I have to do this more carefully. So just positive, bigger than 1. Okay, so these are the corresponding path spaces, and the middle space, which is this one, so that is a path with L2 path with values in H. And I would like to have this embedding, so that of course doesn't work because we have no embeddings of this alpha here, even if alpha is bigger than 2, because it is not a finite measure here. So I just do the usual trick. So I take the intersection with the middle space. And then naturally, if I take here the sum of the norms or the maximum of the norms, the corresponding dual space is this. Okay, so then I have a corresponding Gelfand triple of paths. And now I look at this equation that I want to solve in this path space. So let me go back to the first thing, and this is the end of the motivation. So then this could be considered as an operator on paths with values in the corresponding space, V or H or whatever, or V star. And the same here. So that means we are then looking for, given a path here, we're looking for a solution path of this equation. And now here's a major point. If this A satisfies monotonicity conditions, so it is maximal monotone in the language of nonlinear semigroups, and then if we can prove that this is maximal monotone, but now immediately when you know Markov process, you know semigroups, even on R1, you know this guy should be maximal monotone because it's a generator of a semigroup, and then general theory tells you it is maximal monotone. So this is maximal monotone on path, this is maximal monotone on path. Question is the sum maximal monotone? It is, because we work on this space, and this operator is defined on the whole space. Then the general theorem tells you it is the sum is maximal monotone. It's not as easy as I tell you right now, because we cannot really apply this general theory if you look at it carefully. Okay. But then the sum is maximal monotone, and then if you have coercivity, or dissipativity, depends on your terminology, it is on 2. So we can solve this equation for any path in this path space corresponding to V star. And that's the way how we solve the equations. So the main point, yeah, so in this path space, so any F in this path space has a corresponding path U, which I can plug into the equation, and I get as an image this, done. So we have solved the equation. And then it doesn't matter whether A is linear or not linear, as long as maximum monotone things work. We have a bit of a problem here because we're working in the Gelfand triple, so the standard theorem about this maximum monotone plus maximum monotone gives some maximum monotone under certain conditions doesn't work. So we have to work with a new type of space and then sort of generalize these results from monotone operator theory and nonlinear semigroup theory to this situation. But I will not go into this today because I don't have enough time. I just would like to tell you, I mean, in what sense now, what kind of, as what kind of generator we interpret this fractional derivative for this K. Okay. So again, this is our assumption on K, but which I mentioned before, I don't repeat it. There's a lot of examples, yeah, so the usual ones, Caputo, truncated, and so on, exponential weight, gamma subordinated, and we always have this kind of K. What I forgot to say is that we solved this equation. Sorry that I scroll back for the third time. Don't want to make you dizzy, but you see, we solved this equation really as a differential equation. So we do not go to the integral equation. Of course we can. In the usual way, we can write this as an integral equation, but we solve really this equation. And then we get the solution automatically from the integral equation in the usual way. Right? Okay, so where this kernel appears then in the integral. Okay, so now let me explain how we interpret this generalized fractional derivative with this k. So k is our data, our datum, and then we look as usual, and most of you know this, we have a lot of theory behind this. We take the k, we take the measure, so the k is a label here that refers to this k. So we look at the corresponding sort of distribution function. And by Carathéodory's theorem, we get that there exists a measure, maybe not only sigma finite on this typically, well, it doesn't have to explode at 0, but of course, the most interesting case they explode. And with that, such that the distribution function of this measure is exactly the k. Okay, then by Fubini's theorem, you see immediately that this measure integrates tau infimum with 1, right? So it is even better than a Levy measure, right? Because for the Levy measure, we have this, which is a weak, yeah, so we can sometimes it's stronger. Okay, so now we can, so we have the Levy measure, so then we can use a theory of Levy measures. So we can look naturally at the corresponding Bernstein function, which is exactly this function. Okay, so 1 minus e to the minus lambda t, and obviously this integral exists for every lambda in C plus because of this condition. Okay, so that's it. So we have automatically k comes with mk, comes with psi k. And what is interesting here, if the lambda, this is obvious, if the lambda is real valued, not negative, then this is always a positive function. And we will mainly use this function for non-negative reals rather than complex numbers. Okay, so but now it still is complex. And then by general theory, we know that there is a measure, mu tk, on 0 infinity, such that the Laplace transform is given by e to the minus t times the Bernstein function. There's this beautiful book by Schilling, Song, and Vondracek where you can check this. So now we are dealing with time derivatives, so the corresponding semigroup is just a shift to the right. This is trivial. But now we look at the semigroup in our path space. Okay, we take a function in f, in h. Remember, if this h is L2 0 infinity, with values in h, because the time runs to infinity, right? Even if we want to solve the equation up to capital T, first of all, the clock will run on, even if we stop at capital T to solve our equation. Okay, but there is another reason for that, why we need this the whole time interval. So there's nothing about reflection at boundaries and so on. We just take this time and then we take uniform motion. We take a shift to the right. Okay, so now you can see here why I look at the whole interval from 0 to infinity. Yeah, because otherwise you shift this function. So that means original, I don't know, it's something like this, and then you shift it to the right. And then if the time is over at some time, then the function will be gone. So this semigroup, the shift semigroup, if you look at the finite time interval, will not be conservative, will not conserve mass. That's bad. So we really have to look at the whole time interval, and then from now on, I mean, we always extend our functions on path space. You see this path, they start at 0. Okay, but now we just look at such a path, h-valued path, and we extend it to the whole real line by putting it 0 on the left-hand side of the axis. Yeah, so I do this now without further notice. Okay, so now we can look at the semigroup, the shift semigroup, and we subordinate it with this measure mu tk. So then if you look at this shifts in time, everything is Hilbert space valued at the moment. And then you see immediately it is nothing but the convolution in time. So t is fixed to convolute in time, our function which is h valued. Okay. Okay, and then this is just a side remark, then you can check that the corresponding generator is really this generator. So that means in Fourier space, so if you calculate in Fourier space, it is simply the usual domain as you would expect. So that means multiplication with psi to the psi k. This is the label referring to k, it's not an exponent, at minus IR, and then you multiply with the Fourier transform of u. So that is the domain. So you assume this is an L2 complexified, And then the action is exactly what you would expect, multiplication by this. But that's not enough for us to understand the generator of the semigroup in L2, 0, infinity with values in the abstract Hilbert space H. So this is just a sign that this is the sort of the right semigroup to consider. Okay, so now here comes the most important ingredient, the most important construction we have to do. We want to define a fractional time Sobolev space with values in our Gelfand triple. So I wrote here V. It is not quite precise. You will see when I write the exact definition, because the guys should take values in this small space V, this path, but after differentiation, they only take values in V star. So that's a typical infinite dimensional Sobolev space. When you take time derivatives, then you will end up in larger spaces. So that just comes from the theory of PDE. And this is basically what now I wanted to define. So I'm able to take a fractional time derivative with my function k, and then I look at my alpha, which comes from the space V. Remember, this was L alpha, 0 infinity with values in V intersected with the curly H. So I would like to write down, so this is the spatial derivative, and this is sort of the time derivative, fractional time derivative. Now, to find this space, that was not easy, and we were motivated to look at the space by an old work by Wilhelm Stannard on generalized derivative forms. And so this is the following. So it can be checked. This function UTK, the subordinated one, is a C0 semigroup on curly H, on the space of path in H. But one can also show that if I apply it to a function which is V-valued, it stays of course V-valued. So it's also a C0 semigroup on the space of path on the smaller path space, on the V space. So because it keeps it obviously invariant. So we can also look at the generator there. And that is the key to find this space. So then if we look at the generator of this semigroup restricted to this path space, then it is just by restrictions by general linear semigroup theory. The restricted semigroup has the restricted generator as its generator. So I take all U in the domain of the generator when I consider the semigroup on this path space. I intersect it with the smaller one, and I demand that also the image is in V. By semi-group theory, we know that this domain is dense in V. So therefore, if I make it a little bit bigger, this domain, maybe this one, it's the same operator, it's just a restriction. This is for sure dense in V, okay? So now I can look at this operator on this domain without this restriction. And I look at it not as because now this is a generator on H, so this generally takes value in H in the middle space, in the middle path space. But now if I take the bigger space with the weaker topology, then I can show it's closable there, okay? And now we can just take the closure of this operator, and that's exactly so the corresponding domain, so using the completion, right, with the graph null. And this, we call this space Fk. It's just the domain of the closed up operator. And the K is again a label. And we take the corresponding norm, the graph norm. And this space is exactly the right space for us to solve our equation. And this space, if you look at the construction, is really this, something like this. The derivative in time is in V star, okay? But just we have to take the right space, so close it between, so the right domain, and then close it with respect to the larger path space, and then things work. Okay, so a natural domain now, when I apply this guy to path in time t, so t is just again a label, so it's not a variable. So what do I need? I have to take the convolution first and then be able to differentiate. So that's the natural domain. Yeah, so all U, taking values in V star, doing this, and then you take the derivative, the weak derivative in time, and it should be, so that's weak Sobolev space with values in V star. And that's the right domain, first of all, of my Caputo. And then I also need this weighted space in a second. So whenever I have a space of paths in some Banner space, then I look at the weighted space by putting it in time with this little gamma. And now I can explain our main result. So the result says, first of all, this Fk, this constructed Sobolev space with my fractional derivatives as the derivative is in fact, first of all, in the domain of this guy. I want to stress that all this work is analytically subtle in the sense that you have to all the time fight with domains. You are no longer, when you think of the time fractional derivative as a generator of a Markov process on the real line, you're no longer on the real line where domains can be identified much more easily. But we have now the thing, so the Markov process, if you have a Markov process in mind, this takes values in the Banach space. Okay, so then domains becomes much harder to identify. And this is the main work, to find this right domain, and I claim this is the right domain, and then prove first of all this, which is not difficult. And then to prove that actually our lambda k, which is the operator which extends, right? This lambda k extends to this space, so extends x on this path space. So everything is on path space. That's another point. And then you can just calculate that this lambda k, this operator, is exactly, so that this is in a sense the restricted generator of our subordinated semigroup is exactly the Caputo. Sorry, not the Caputo, the generalized, the case general, so the generalized time fractional derivative with a minus sign. And here comes another observation, because now we have always this triple between the paths, V star and V, yeah, then we can look at the inner product, yeah, in this two path spaces. So this is sort of, if this is not there, this is exactly the inner product between V star, so my path space from 0 to infinity, and then this is the sort of the duality between the two path spaces, okay? So I can look at this. But now comes the point. So for any gamma strictly positive, if I put this weight here, yeah, one can prove that this is bigger or equal to psi kappa of gamma times this. So it's strongly dissipative. And the dissipativity constant, yeah, as an operator. Yeah? So if you think of just a moment we are in Hilbert spaces, then this is some generator, and then this is a statement about a spectrum. The spectrum is bounded below by a strict positive constant. And this you call strong dissipativity. That's why we call it strong dissipativity. And the dissipativity constant can be calculated by the Bernstein function at this gamma. So this is true for every gamma. So this weight, yeah, shows up in this dissipativity constant here. So that's the dissipativity of the generalized fractional derivative considered on a path space, yeah, path space in the general Gelfand triple Banach space, or however you want to describe it. So I have a little bit of time to give you some idea how to prove such things. And the first one is easy on a calculational level because it's the same proof as in one dimension. So just think of the Hilbert space to be R1. It's the same proof. The only thing you have to control the domains, and that's the problem. Otherwise, it is exactly the same as the proof that you just calculate the Laplace transform from both sides. And you do this first for very nice functions u. Now here comes the technicality, the technical problem. So first of all, we do it for very nice functions u, and then we extend it to the whole space fk. Yeah? So, and then you have to see that the operator here is uniquely determined on this nice space of functions. So here we take this space of functions. So now whatever you want. Okay, but we have to show that it's an operator call for the lambda k, otherwise we cannot go up to fk. Yeah, otherwise no chance. And there we use some trick that we show that this domain of nice functions is invariant under the semigroup, and then the general theory tells you if this space of function is dense in the underlying Hilbert space, which is L201H, first of all, in the first step, then it follows that it's also an operator call, so dense in the operator norm in the corresponding domain of the operator. So this is the technical thing to be solved, to do this first on the Hilbert space and then of this on the space fk. And otherwise it's the usual proof. You take the Laplace transform of this guy, not, of course now a function value, but there's no problem, and you show it is multiplication with pi k lambda, like in the Fourier picture. And then you take the right-hand side, you take a derivative, you do exactly the same calculation, you do it in a weak form, and then you find exactly the same formula up to the minus sign. So then altogether, the Laplace transform is the same as this one, up to minus sign, and so you conclude the result. Up to domain question, and I want to stress this. And I must say there are some referees of this paper, they did not pay any attention to this point, and then of course this is proof is trivial. But you have to pay attention to the domain, otherwise you prove nothing. Okay. Right, and then the strong dissipativity, maybe I have 2 or 3 minutes to explain that to you. And that's very simple. So it's exactly this lemma. So you look at the subordinated semigroup, again, as a semigroup on this path space, and then you look at the Laplace transform of it, okay? And then it is very easy to show that it has this kind of property. So first of all, again, we work on H, and then we go into the Gelfand triple. It's always 2 steps. And this, again, is domain problems, but they can be solved. So now I only do it on H. Yeah? And then you can see the dissipativity on H already. So this is a strongly contractive semigroup, because as I stressed, this is positive. Yeah? So gamma positive, this is a positive number. So it's e to the minus positive number g. So that means you can read off the spectral gap already here. And really the proof is you just differentiate the thing and then you get the dissipativity formula. And now here you see of course you can imagine that somehow this will not preserve the mass, somehow this UTK for T positive will not preserve the mass, strictly positive, will not preserve the mass. But if we do, we'll preserve the mass, but that's what we want. We want to make mass smaller. So if we take this weight, it really becomes smaller in this space. And that's the observation. And the proof is then trivial. Now you look at this guy, you write the definition, use the definition. Now you think, okay, here you have to take the Hilbert space value of this guy, which you integrate, you take the norm squared, but it's a usual Roeckner integral, so you can interchange, yeah, the integral with the norm squared, the Jensen's inequality. So you get this. So now you are in the real world. So it is very simple. So you have just convolution of 2 functions depending on time. Take the Laplace transform of it in time. So this is just a product of the Laplace transform. So I've written down this here at point gamma and the Laplace transform of this guy. But the Laplace transform of this guy we know. Remember, this was by this nice book by Schilling and Vondracek. We have exactly this guy. Yeah, this is just what I said about this, the definition of this measure, basically. Yeah, and then you have to write down the Laplace transform of this guy, which is just this. Yeah, at point gamma. So you're done. And then differentiating that, I can quickly show you. Then you get the dissipativity formula. Okay, so first of all for the generator, but by the other theorem we know this is minus the fractional derivative. And we are done. So then we get exactly the opposite inequality. And to prove this now, so you get from the contraction property of the semigroup, you get spectral gap if you like. It's not the self-adjoint operator. So I'm not doing any spectral theory. I just use this very simple fact that you get such kind of an inequality for the generator. And you can see it. I just write down the left-hand side. Then I know this is just a derivative of this minus this 1 over epsilon. So I write this apart, then you see there's no absolute value, so I can make this bigger by using what I've just done. First do Cauchy-Schwarz, then I do Cauchy-Schwarz for the integral, I get a square here with a one half there, then I use the contraction property, so I know that this is less than this. Then I put things together with this together, so I get this. I take epsilon to 0, and I get really down here the right quotation mark spectral gap. So this gives me this kind of dissipativity when I work on H. And now I replace this by my minus d by dk, which I proved here. We proved here, just that. And then I plug it in, and I get exactly what I, I get exactly what I just plug it in, I get minus here, so it's multiplied by minus 1, and then I get the dissipativity. So one last remark about how can you find that? I mean, if you're expert on this this kind of derivatives, and you know they're generators of something and so on, no connection to Levy processes, then still to guess this formula is maybe not so obvious, but I think you can. Yeah? So that's one thing. But I must admit, we found this in a completely different way, namely from the point of view of PDE. So if you look at your fractional equation, so I go back to page 1, just to give you how you can get this idea. So if you go to such an equation, you have a parabolic equation. So there's a general trick to make a parabolic equation more dissipative by replacing the solution by e to the t some constant times the solution, okay? And then, well, you write the new equation, and this operator A, because it's nonlinear and depends on time, you just get another operator by doing this transformation for your solution, yeah, because you have to put it in here, transformation. You get a new operator, because but you allow time dependence, and you check the new operator you get satisfies the same condition as the old operator, okay? And then, when there's a normal derivative, yeah, then when you have u replaced by e to the minus t gamma, then you get one term by using the product rule that gives you dissipativity into the equation. Okay, that's a usual trick in PDE. With the fractional time, impossible. You don't have the, of course, you have kind of, well, product rule, but it is a sum, it's a series, so it is of no use at all. So we thought about the fact, okay, doing this, I mean, you use it also in ODE in order to, I mean, when you want to prove contraction, you just change the norm by taking the soup over t, but after doing this multiplication with e to the minus t gamma, yeah, then you get a better contraction constant. We all know that, but it's not possible to do this for fractional time derivative. However, the exact analog of doing this is to analyze this equation not in L2 with respect to dt, but in L2 with respect to e to the minus gamma t, and that's how we found it. So just intuition tells you it should be this trick, multiplying e to the minus gamma t, it should be done in integral form because your fractional derivatives is something in integral form, right? And that's why then we get this, I scroll back to the point, we get this with this, only with this constant, yeah, with e to the minus gamma. So that's why we found this, and then when you see the semigroup contracts nicely, then you know, okay, the generator must have a spectrum gap, must be dissipative, and that's the observation. It's all not so difficult apart from the domain problems. So now I should stop. Thank you very much.
Okay, so thank you very much for a very interesting talk. Any questions, any comments, please? I will then maybe ask you, say, of course, and it's well known, yeah, it's very difficult thing to